Hello my friends. In the next two rather short videos we are going to conclude our discussions about normal subgroups. Now in the last video we proved using a pedestrian approach that the group A3, the so-called alternating group on three elements, is indeed a normal subgroup of the symmetric group on three elements. And this is actually the easiest non-trivial example in the non-commutative case for a normal subgroup. And while elementary, this was still some work. We still had to write down the conjugations of permutations to see that this is true. Now, this proposition here contains a very useful result that in this case yields that this must be a normal subgroup without any further ado. So, as always, G is a group, N is a subgroup of this group G, and we suppose that the index of N in G is 2. Then this proposition asserts that automatically N is then a normal subgroup of G. So, in words, subgroups of index 2 are always normal subgroups. And this is also true for infinite groups, so we don't need to be the order of G to be a finite number. This is always true. All right, let's take a look at the proof. If you remember this lemma we formulated, this contains three equivalent conditions for a subgroup to be a normal subgroup. And it turns out that in the context of this proof, this condition here is indeed the most useful or easiest to check. So we need to check or show that this is true for every element of the group, so that the left coset of G is the same as the right coset of G, always with respect to the subgroup N. So first case, if G itself is an element of N, this is trivial because then Gn is simply N, which is the same as Ng. We proved that a long time ago when we talked about equivalence relations, or you can check this for yourself in a minute if you want to. Now if G is not an element of N, then the left coset of G with respect to N cannot be N itself. This is also pretty clear, but let's assume those were the same. Then G, which always can be written as G times the identity, which is an element of this left coset because N is a subgroup, hence contains the identity. But if we suppose that this here is equal to N, then G itself would be an element of N, which it is not. So this contradiction shows that this here must be true. And now we use the assumption the index of N in G being 2 means exactly that there are only two distinct cosets. So one coset, of course, is N itself, the left coset of the identity. And since this is not equal to N, it must already be the other of those two cosets. So N and Gn form a partition of G, which means that G can be written as the disjoint union, that's that symbol here with the dot inside of the union symbol. G is the disjoint union of N and Gn. Now this here always means the left index, so the number of different left cosets, but we proved on problem set number, I don't know, that left index and right index are always the same. So if the left index is 2, then the right index of N in G is also 2, meaning that there are only two distinct right cosets. So, and you can see by the same argument that Ng cannot be the same coset as N. So again, G can be written as the disjoint union of N and the right coset of G with respect to N. Now, but this here means that the complement of N in G, meaning all the elements that lie in G but not in N, must be the left coset Gn. Because this is exactly what this disjoint union here means. If I take away N, then this is all that is left. And by exactly the same argument from this equality here, we find that the complement of N in G is also the right coset of G with respect to N. But then, of course, N complement and N complement here are the same sets. And from this, it follows that Gn is the same as NG. This finishes the proof. Now, in the case of a finite group, so when this order here is finite, the index being 2 means exactly that the order of the subgroup N is half the order of G. Why? Because by Lagrange's theorem, the index is nothing but this quotient here, the order of G divided by the order of N. And if this here is 2, this means exactly that here the denominator, I think, is half of the numerator. I hope this was the correct order of these terms. And this is very useful because, as pointed out in the beginning, we had to put in some work to show that A3 is a normal subgroup of S3. But if we use this proposition combined with this remark, if you wish, we have in one line that this here must be a normal subgroup because the order of A3 is 3. This was simply the cyclic subgroup generated by a 3 cycle. And 3 is half of the order of S3 because this is a 3 factorial, so 6. So without any further work, we see that this is true, and the same applies to this situation when we take a look at the dihedral group of the regular n-gon and the cyclic subgroup generated by the rotation by 2 pi over n, or 360 degrees over n. Then the order of this here is clearly n, because the order of R is n. If I rotate n times, I for the first time get the identity. And the order of the whole group is 2n, so this is half of the order of the whole group. So again, using the proposition combined with this remark, we see that this here is normal in Dn. All right, that's it already for this week's lesson. I hope you enjoyed that. Please leave a like or subscribe, and I hope to see you next week. Bye bye.